Welcome to CEDA-Labz. Here are the answers to the questions asked in the previous tutorial. Our question was to design this state machine. It is a mealy state machine, and here is the code for same. This is memory block, where if reset is low, present will be B, or else it will be equal to next state. Further, this one is decoding logic part of the code. Here, it is decoded what will be the next state in all cases of input. For example, in case of A, when input is 0, next state is B, and when input is 1, next state is A itself. Similarly, it is written for rest 2 cases, of B and C too. And this one is output logic coding part. Here, output is evaluated depending on input and present state. In case of A, when input is high, output is 0, and when input is low, output is high, that is, 1. Rest 2 cases are also written in same manner, considering the state diagram. Here is the test bench for the same. As we used to do, module name, port declarations, module instantiations, clock initialization and generation, input conditions with delays, and termination via end module. Let's come to our next topic, which are task and functions and delay models in Verilog. A designer is frequently required to implement the same functionality at many places in a behavioral design. This means that the commonly used parts should be abstracted into routines, and the routines must be invoked instead of repeating the code. Most programming languages provide procedures or subroutines to accomplish this. Verilog provides tasks and functions to break up large behavioral designs into smaller pieces. Tasks and functions allow the designer to abstract Verilog code that is used at many places in the design. Tasks and functions serve different purposes in Verilog. Both tasks and functions must be defined in a module and are local to the module. Tasks are used for common Verilog code that contains delays, timing, event constructs, or multiple output arguments. Functions are used when common Verilog code is purely combinational, executes in 0 simulation time, and provides exactly 1 output. Functions are typically used for conversions and commonly used calculations. Tasks can have input, output, and in-out arguments. Functions can have input arguments. In addition, they can have local variables, registers, time variables, integers, real, or events. Tasks or functions cannot have wires. Tasks and functions contain behavioral statements only. Tasks and functions do not contain always or initial statements, but are called from always blocks, initial blocks, or other tasks and functions. Tasks are declared with the keywords task and end task. Tasks must be used if any one of the following conditions is true for the procedure: there are delay, timing, or event control constructs in the procedure has 0 or more than 1 output arguments, the procedure has no input arguments. Here is the task declaration syntax. Task is declared with the keyword task, followed by the task name. These are the input and output declared in a task. They remain local to the task. The desired statements are written inside begin and end block. And task is terminated by the keyword end task. Here is an example using task. We started with keyword module. Module name is top, followed by a port list. We want to do 8-bit XORing operation of variables A, B, and C, D. The output A, B XOR and C, D XORs of 8-bit. Similarly, input variables are of 8-bit. Clock is defined as input. And here output is defined as reg type, as in behavioral modeling output is of reg data type. In this example, there are 2 always block for calculating the bitwise XOR operation. Both the always block will trigger at same time. In the first always block, when control reaches inside the always block, the value of inputs A and B will be given to task bitwise XOR. The moment this task bitwise XOR is triggered inside this always block, the values of A and B will be passed to the task. Here, In this task, A and B will be copied to M and N input variables which are local to the task. And this statement MN XOR is calculated, and immediately its result is passed back to the always block from where it was initiated. And AB XOR will get back the calculated value. Similarly, this will happen with another always block too, and value of CD XOR is calculated. And here is the test bench for the design block which was described in the last slide. Module starts with the keyword module, followed by module name. Ports are declared here and design block module is instantiated. Further, clock is initialized here within initial block and generated with a duty cycle within always block, as we used to do. In this initial block, some 8-bit input conditions are mentioned to test the functionality of the design code. And initial begin block is terminated by keyword end. Similarly, module is terminated by keyword end module. Functions are declared with the keywords function and end function. Functions are used if all of the following conditions are true for the procedure: there are no delay, timing, or event control constructs in the procedure returns a single value, there is at least one input argument, there are no outputs or in-out arguments, there are no non-blocking assignments. Here is the function declaration syntax. The function is declared with the keyword function. Function doesn't pass the value, it simply returns the value. So, function doesn't need any output variable. Function statements are declared within begin and end. Here is an example using function. In the given example, desired module is calculating the factorial of a number. Module is declared with the keyword module, followed by module name as factorial. It has two ports. The output variable, fact, is declared with keyword output. And variable, upper, is declared as input, which is of 3-bit size. Since we are using function inside the always block, the output port is declared as reg data type. When input port, upper, will get a value from the test bench, then this always block will trigger. Whenever a function is declared in a module, then there will be an internal register created of function name. In a given always block, when function is triggered, then value of upper is passed to function factorial. This value of upper is copied to k. There is a declaration of local register I with the keyword integer, which is used in for block for calculating factorial. In this given for loop which is defined within begin and end, I is initialized to 1. The loop will count in a looping fashion, and value of k will immediately return to function calling statement 1 by 1. Test bench for the same example. We started as usual with module and module name. Output declared as wire and input declared as reg. Then, design block module is instantiated with a port list. And, within initial begin block, values of input testing condition are provided with a delay. And, this is terminating end for begin block. And, terminating end module for module. Functional verification of hardware is used to verify functionality of the designed circuit. However, blocks in real hardware have delays associated with the logic elements and paths in them. Therefore, we must also check whether the circuit meets the timing requirements, given the delay specifications for the blocks. Checking timing requirements has become increasingly important as circuits have become smaller and faster. In this section, we will discuss how delays are controlled and specified in Verilog modules. There are 3 types of delay models used in Verilog: distributed, lumped, and pin-to-pin, also called path delays. Distributed delays are specified on a per-element basis. Delay values are assigned to individual elements in the circuit. An example of distributed delays is shown in this figure. Distributed delays can be modeled by assigning delay values to individual gates, or by using delay values in individual assigned statements. When inputs of any gate change, the output of the gate changes after the delay value specified. These examples show how distributed delays are specified, in gate level and data flow description respectively. In gate level, delays are provided within gate instantiations, after the gate name. And, in data flow definitions, delays are provided after a sign keyword. Distributed delays provide detailed delay modeling. Delays in each element of the circuit are specified. Lump delays are specified on a per-module basis. They can be specified as a single delay on the output gate of the module. The cumulative delay of all paths is lumped at one location. The example of a lump delay is shown here. This example is a modification of previous example shown in distributed delay model. In this example, we compared the maximum delay from any input to the output, which is 7 plus 4 equals to 11 units. The entire delay is lumped into the output gate. Here is the Verilog code for the same. As we can see, in this example, the entire delay is associated with one gate only. Lump delay models are easy to model compared with distributed delays. Another method of delay specification for a module is pin-to-pin timing. Delays are assigned individually to paths from each input to each output. Thus, delays can be separately specified for each input or output path. We take the same example and compute the pin-to-pin delays for each input or output path. Pin-to-pin delays for standard parts can be directly obtained from databooks. Pin-to-pin delays are also known as path delays. Path delays are assigned in Verilog within the keywords specify and unspecify. The statements within these keywords constitute a specify block. Specify blocks contain statements to do the following: assign pin-to-pin timing delays across module paths, set up timing checks in the circuits. The specify block is a separate block in the module, and does not appear under any other block, such as initial or always. Inside specify blocks, statements can be described in two ways: parallel connection, full connection. Parallel connection is specified by the symbol equals greater than, and its syntax is shown here. In parallel connection, each bit in the source field connects to its corresponding bit in the destination field. If the source and the destination fields are vectors, they must have the same number of bits, otherwise, there is a mismatch. Thus, a parallel connection specifies delays from each bit in source to each bit in destination. This figure shows how bits between the source field and destination field are connected in a parallel connection. Here is a Verilog description of an example for parallel connection. As usual, we started with module and module name followed by port list. These are the port declarations, out declared as output port, and A, B, C, and D are declared as input ports. Internal connections, E and F, are declared as wires. Here are the gate instantiations according to the figure in the slide 23. And, here in specify block, we specified path-to-path delays between input and output ports via parallel connection. From A to out, delay is 3. B to out, it is 5, C to out, it is again 3, and D to out, is 5. Specify block is ended by end specify, and module is terminated by end module. Here are some more examples showcasing parallel connection. In first example, A and out are both 1-bit variables and delay between the two is 9. In second example, vector connection is represented. A and out are both 4-bit variables. 0-bit of A is connected to 0-bit of out, and similarly, its all other bits are connected to respective bits of out with a delay of 9. Just because they both have equal number of bits, it is a valid connection. And, all of have them same delay, so we can also write as A to out equals to 9. But, if the number of bits would have been unequal, it would be an invalid or illegal connection. As you can see in this particular example, A is a 5-bit variable and out is 4-bit variable. Bit width does not match, so connection can't be done. A full connection is specified by the symbol greater than, and is used as shown under the heading syntax. In a full connection, each bit in the source field connects to every bit in the destination field. If the source and the destination are vectors, then they need not have the same number of bits. A full connection describes the delay between each bit of the source and every bit in the destination as shown in the figure. Here is a simple Verilog code for full connection. Here also, everything is done the same. Just there is difference in specify block where both A and B are connected to out with a delay of 9, as we can see from the figure in slide 23. And similarly, C and D are connected to out with a delay of 11. The full connection is particularly useful for specifying a delay between each bit of an input vector and every bit in the output vector, when bit width of the vectors is large. This example shows how the full connection specifies delays very concisely. Now, let's move into the flashback. In this tutorial we study tasks and functions, their difference and some Verilog description of the same. Then, we studied DelayModels, specify blocks and parallel connection in full connection within specify blocks. Here are some questions for you. I hope you'll be able to answer them.